Good morning, all. This is our last course, and I'm glad that we have plenty of students in our classroom already. Crowded is already only 8 students in the classroom. One of them is dropped. No, 7. Abdurrahman, Efe, Mahmut Ramadan, Muhammed Najati, Ozan Akkoç, Right, Hassanah, Yusuf Selim. Bir de Hamza var. Hamza dropped. Hamza Muhammed. Now, you can see that if it is last course, I have to also summarize something, but I also would like to complete the program. What the basics of the control course is kind of system. Your wish, objective, that's the objective here. But that is the result. That is the result. That one is system. But this one here is controller. That's the one you are responsible, controller. The last 2 weeks or so, we concentrated on controllers, but we never forget main objective of our control system. One of them are your system should reach a final value. It should be as good as possible or as precise as possible. That means your steady state error should be 0 or almost 0. Steady state error. What's error, by the way? Error is this one. That's the one error. The difference between your wish, the difference between your wish, RS, and your result, CS. Ogata use CS, Hoft use YS. Both are acceptable. Okay, so that's the error. Error should be 0 or very near to 0. But also the maximum overshoot should be, or oscillation should be as low as possible. And also the response time should be as small as possible. So we require a fast response. All right. But in the meantime, we have seen that for controller, we have K, also integral and derivative. This is called PID. But also we have seen that if you know the system, we can add 1 0 and 1 pole to the system. Then we have seen that lead compensator and lag compensator. Lead and lag compensators. These are the you have learned. I'm just going to review the first, just warming up the lead one. If you have a system like this, and if you are not happy about the solution, which that point is not very good, then we add 1 0 and 1 pole to the system. That one pole and one zero, you can see that we add a zero here, zero over there. The second method I taught, you have completed the home assignment, and we have seen that the GC we add was that, I just review, GC we add that so that's lead alpha smaller than 1. That means you are actually putting 1 0 here. Kırmızıyla göstereyim. Now your system has got a pole already here, and you are not satisfied, you are not happy about that pole. You would like to get rid of that pole. So you are adding a 0 here. 0. As long as you add a 0 here, you get rid of that pole. However, you have to also, you can see that you are going to add 1 0 here and one pole over there. Pole is far away from the origin, but the angle condition should be satisfied, and you already obtained for home assignment that we are also adding a pole here. As long as you add a 0 and pole, your system becomes very, let's say, stiff, and the waveform was, the original waveform was this, and we improved that one. We discussed that one. This is lead compensator. In lead compensator, you are adding 1 0 for lead. You are adding 1 0 somewhere there, which is on top of the pole, and one pole here. That is lead. However, for lag, you are happy about the transient, but you are not happy about the steady state. Then you add a pole here, and very near to this, a 0 here. Since these two are very near to each other, so that reflects that it doesn't change the original location of the poles. And that one, the follow my cursor, please. For lag, you are adding here a pole almost 0, 0.005, you remember. And then, of course, almost to origin, let's say. And also, that 0 you are adding is very near to this. Finally, for lag compensator, we have seen that we are quite happy about these 2 points. Then we are going to improve the steady state loss, steady state error. Then you are going to add a 0 here, almost 0, almost to origin. You are adding a 0 to almost origin. And very near to it, you add a pole. And the root locus also, this is the one, for example. Beta is always giving you the factor reduction of the steady state error. So this 10 is 10 times reduced the steady state error. Okay. And you can see that the relationship between that beta here down is the same equation, by the way. Same equation. Hemen yazayım onu da. I just repeat. It's not a new topic. GC lag compensator. And you can see here that we are adding actually a 0 and pole. Pole is almost origin, very near to origin. And that one is also very near to this. And it's obvious that when you add those here, your curve is not changing. But what's happening actually, that pole and 0 couple here, and then without changing the curve. That is what lag compensator is all about. And also the compensated system reduced the steady state error. Log lead compensator is the combination of these two. Now let's go back to our last week's course. I just repeat, I'm sure you, while you are solving your home assignment, it's not it's a design project. You understand how could you design a lead compensator. Now let's go back to PID parameter definition. PID parameter, it's another design problem. I'm going to, probably this afternoon, I'm going to give you a home assignment, and you are going to give those home assignment to me. It's 10 point, by the way. It's valuable. So, but make yourself. Don't ask your friends. Even you can ask me. You can write. Those who write me, I answer. Uh, I never delay. So I can help you to solve it. All right, home assignment. This is my duty to teach you something. Okay, but ask your friends as well. Ask the people who knows it beforehand. But try to understand how could we define PID parameters. Starting with moderately correct proportional, integral, and derivative values are valuable, very important. Why I'm saying moderately, we have already seen that the first initial values developed by Ziegler-Nichols are, are not fully covering the best control performances. But it's a good starting point. You see, you have three parameters you have to define. So it's very difficult to obtain which one is the one correct one and things like this. So what you do, this is the time domain equations, for example, is important. You never forget that. You never forget that. You are adding actually a KP here and KI here and KD here, but your controller transfer function, which error over the output, input is error, output is the controller output, and then you are, of course, I'm not going to derive that equation again. I even ask in the midterm exam as well. all you have to do, either you are going to calculate Kp, Ki, and Kd, or Ti and Td values. But one thing we never forget by looking at the final equation, we are actually adding two zeros and one pole. For lead compensator and lag compensator, we are adding one pole and one zero. But here, we are adding two zeros and one pole. It's what PID is all about. And if you know nothing about it, these are, of course, well-known parameters you already defined. If you test your system with a step function, you give a step function to your system. If you have output like this, that means either your system is second order, third order, and however, its damping is above, damping is heavy, therefore no oscillation occurs. Or first order system. If you have output like this, then use Ziegler-Nichols first method. Measure the L here. So prepare a tangential line, tangent line to this curve. This is the output, that one. And look about the L here and obtain the T here. T is the line crossing the actually step value. And then if you measure those or calculate those, or in model you use it, in model you can use it. For PID parameters, you can use that table. However, if any oscillation occurs, then if any oscillation occurs, that means you are increasing your proportionality constant while oscillation gets up and up and up again, then it reaches the continuous oscillation. That means roots are now located on the j omega axis. Roots are located at j omega axis. Continuous oscillation, sinusoidal or cosine function output. Then obtain K value. K value, KCR, it's called. When you obtain KCR, then also measure the periods here, the function. So if you know the period PCR and KCR, use second Ziegler-Nichols method. Table is ready. So 0.6 KCR, 0.5 PCR, this is TI and TD. And the equations here, before solving that one, I'm just going to write the equations again. Then that's what we use. Don't forget. I'm sorry. Buraya sığdıracağım çocuklar. Ya da bir önceki sayfada bakayım değer daha mı fazla? Hayır. Burada var. Bakın. Biraz da inceltelim kalemi. Yazdım daha evvel ama yeni dinleyenler için veya yeni çalışanlar için önlerinde olsun diye söylüyorum. For those who listen that course material and try to learn it, then might use it. GCS is equal to KP 1 plus, you remember that one, PID 1 over TIS plus 1 over, I'm sorry, TDS. O da eşittir. Buraya aşağı yazıyorum. According to Ziegler-Nichols second rule, 0.6 times KCR bracket 1 over, I'm sorry, 1 plus 1 over 0.5 PCRS plus 0.125 PCRS, or 0.075 KCR times PCR times S plus 4 over PCR square over S. So now we are adding two zeros which are equal each other. You see, and the value of 0 is equal minus 4 over PCR. And also we are adding one pole. Result is this one. So we are going to use those equations. Time to time I can come back and refer it. I remember I solved this problem. I have already drawn the curve. The root locus of this one is something like this. I just still repeat. One of the pole is located in 0. One of them is minus 1. The other one is, I'm sorry, kafamda 5 var, gitti. Minus 1. And the other one is minus 5. Minus 5 is not the one which doesn't affect the system. It doesn't affect to the system. These two are dominant poles, these two, and the curve is going to be something like this. The root locus curve. When you increase the value of k, then you, in order to obtain this value for this point, if you measure k, if you obtain the KCR, which we obtained that one, it was 30, remember that. We used Raoult-Hurwitz method. And as long as you obtain that one, you already obtain KCR, and then you wrote the equations. I remember that one. I repeat for those. I come back to this figure. So we obtain KCR by using Raoult's who with stability criterion, we obtain that. And as long as we obtain this one, we wrote the equation. You remember that equation. So KCR is 30 already obtained. And the transfer function delta'yı direkt yazacağım çocuklar artık. Yani geçen ders yaptım çünkü bunu. Delta is equal to ne başladı oynama. I'm planning to ask one examination question from this chapter as well. If you solve your home assignment properly, you can also answer the examination question as well. I'm sure those 11 students in my classroom are going to be successful if they carefully follow me. So delta was equal to 5s plus Kp, Kcr, which is 30, equal to 0. And if you write S equal j omega, since it's already j omega axis, that one is j omega axis. If you put S equal j omega, you are going to obtain that system has got 6, 5 minus 5 minus omega square plus j omega bracket 5 minus omega square, which is equal to 0. Equal to 0. If it is equal to 0, that means omega square is equal 5. Only if omega is equal 5, only then this equation becomes available, becomes 0. Burayı anladınız değil mi çocuklar? Çok daha fazla zaman kaybettirmek istemiyorum bilenlere. Çünkü geçen ders we have already discussed that one last week. J omega, şuraya bir matematik yapayım acık hadi. J is equal to E üzeri JP. O da eşittir cosine pi plus J, sin pi. Sin pi. Bir dakika. Eyvah. Bir logaritmadan, bir trigonometri cetvelinden bakar mısınız? Belleğimden birdenbire gitti. Ama kontrol edeceğim şimdi. Siz yazmayın. Aa, bundan da. Bu değil. Ters. Ters yazmış. Sin pi plus j cosine pi. Bu zero'dur. Bu 1'dir. Dolayısıyla c equal c. Tamam mı? Şimdi ama g square is minus 1. Ona göre de you can put s, for example, s to power 3 is equal to minus s square, sorry, plus, minus. S square is minus 1 here. S power to 3 is equal s times, pardon, s power to 3, s power to 3 is equal s times s square. That means j omega times j, j, j square minus omega square. Çocuklar detail'lara girmek istemiyorum aslında artık bugün. Overlook etmemiz lazım. Ama yazdım artık. S times S square olduğuna göre S yerine C omega koyduk. Burada C omega square de eksi omega square'dir. C square minus 1 olduğuna göre if it's a minus 1. Minus omega square'dir. Tamam mı? Neticede bu you are obtaining this one, this equation and omega karekök 5. Peki I have a question. Omega'yı buldum. PCR'ı nasıl bulacağım? Period. How could I obtain the period? Come on, my good 11 students. If you know the frequency, how do you obtain the period? Uzatmayayım. Omega is equal to pi f. O da eşittir 2 pi over t. Buradan t o da eşittir. Bu kitapta PCR diyor. Bulunur. Tamam. I continue. If you give, this is a typical teaching logic. If you discuss details, your students might lose main object. So I come back. This is the problem we are going to solve. This is the problem we are going to solve. We obtain that KCR 30 is the one, but what we need also VCR. But then of course it's since the curves, the poles are already located in j omega axis, so for delta we put j omega. When you put j omega and solve it, then you obtain omega. When you obtain omega, from omega you obtain t, period, PCR. As long as you obtain PCR, you are going to use those equations. You already obtain PCR, you already obtain KCR. So either use that equation or that equation. That will tell you TI, that will tell you TD, and that is your KCR. So we are employing that equation. As long as you employ that equation, it's going to be the double zero is going to be 1.4. You remember that last week we have done that, and we are adding this one as well. As long as we solve it uh, and also multiply with those, we are going to obtain the total transfer function of it. You could draw your root locus if you want. I will tell you, if you draw the root locus, what are you going to do? What are you going to find? That is the one you are going to obtain. Look, so the pole, you located a zero, double zero here. Nerede o? Bir dakika, sakin. Biraz büyüteyim önce. Heh. So we have one pole here, one pole there, origin, double zeros. Sorry, double poles at origin. Benle beraber misiniz bilmiyorum. Are you following me? I'm going to ask you a question. What what what this picture is representing? So we have already obtained that 1.4 is the double zero. Nerede 1.4? Bakın burada. Can you see that? Double iki tane biraz daha büyüteyim göreceksiniz. You can see that when I make it even bigger than this. Double zero. Bakın iki tane daire var. İki tane. There are two circles here. Double zero is located here. Biraz küçültelim bakalım şimdi bunu. So now that double zero, and also we have one pole in a minus one, and also another pole is minus 5. So while we are increasing k, actually this pole is moving to this zero. Kırmızıyla göstereceğim şimdi. Pole is moving in this direction, and we all know that the traveling of the poles ends at zeros. So that double zero, poles are moving like this, and these are no effect at all. It's far away from origin. However, these two provide that kind of curve. Who is going to interpret that one? Are we happy with this curve? This is zeta 0.3 curve. Although zeta is slightly getting better, but that 0.3 is very low. We are not happy. Why we are not happy? I'm going to come back to that curve. Unit step response curve designed by use the Ziegler-Nichols tuning rule. The second method we use, however, the tuning rule is giving us something not acceptable, although it's giving us some idea. Imagine how difficult to predict those values. We have three values here, and you are just starting. It's difficult to predict those. So Ziegler-Nichols giving us a kind of starting point. Tamam mı? Starting point. Bu bizim için başlangıç noktası. Bulduğumuz değerler başlangıç noktası. That double zero is our starting point, and that, or this PID is our starting point. And if we draw the step response, you can see that 60% overshoot. You can see that 40, almost 12 seconds settling time. You can see that 60% overshoot, and you can see the settling time is somewhere 12 or 10, more than 10. which is not acceptable. What are we going to do then? That double zero is not, of course it is good, is a good starting point, but we are not happy about it. So far, I think we came last week here. What you are going to do, you are going to design a new double zero. If you put that double zero somewhere there, yeşille koyayım, bir şey başka renkte göstereyim. If you, yeşil her zaman Murat rengidir. Muradımız olsun. Mesela şuraya double zero'yu koyarsak, bir zero buraya, bir zero daha var. Kaça koymuşuz? Ben hatırlıyorum. 0,6 gibi hatırlıyorum. Bakalım. 0,65'e koymuşuz. 0,6'ya koy. Fark etmez. Bunu kim yorumlayacak? Buraya 2 zero'yu buraya koydum. Ne olacak acaba? Çocuklar şunu unutmayın. Türkçe söyleyeceğim. I'm going to repeat in English. Şunu unutmayın. Root locus köklerin, Türkçesi köklerin yer eğrisidir. Yani kökler yavaş yavaş yer değiştirir. Ama biliyoruz ki pollardan başlar, yani orijinal sistemin pollarından başlar ve zero'larında biter. Sistemin zero'larında biter. Şimdi demek ki benim bu koyduğum çift zero bitiş noktası. Tamam mı? I'm going to repeat in English. We all know that the root locus curves starts with the system's poles. System pole, we have double poles here and also one pole over there. Başka? Eksi 5'te. There is another pole here. These are original system poles. So what we actually are, buradan yürütmem lazım. Kırmızıyla şunu da çizivereyim. Sonra çalışırken şey olmasın. Bu buradan yürüyor. Ve 6 olduğunda mesela k equals 6, one pole is here, the other pole, sorry, follow my cursor. Şimdi yeşili eklemeden kırmızıyı konuşuyorum. One pole is here. When k is 6, one pole is there, which these are far away from origin. One pole is there, the other pole is there. So while you are increasing k, you can see that it's parallel to constant zeta curve. So you are not going to improve you haven't got any chance to improve your overshoot. You haven't got any chance to reduce the overshoot. While we are adding those green 0.6, so we are adding add double zeros, s equal minus 65. Tabii bu kitap bunu 65 eklemiş. You can also add 60.6. It's all right. Of course, they know it's much better for 65. All right. Now, what's happening now? If we add double zeros here, we all know that the journey is going to start from zero. sorry, from poles and ends up with zeros. So these two poles are going to move towards those zeros, and that, sorry, follow my cursor, please. These two poles located here, are trapped by these two zeros here. So these two couples, but instead that pole and this pole becomes free, and these two are constitutes a root locus curve somewhere there. So green line here, green line çizeceğim şimdi buraya. The new case is going to be ikisinin ortası 1 ile 5'in ortası kaçtır? 2,5 mudur? Tam ortası. Evet. Şöyle sanki ikinci dereceymiş gibi bu ve bu buradan başlıyor. Journey is starting -5. The other one is starting. So when you increase k, they come to here, and then you can select a correct point. For example, for 45 degree, for example, you can select. Yeşil istemiyorum artık. Siyah istiyorum. For example, one point here, the other point here falls, which is very nice. The omega is high, sigma is high. Sigma high means your settling time is low, so it's improved. That figure is showing that one. That figure is showing this one. So we are adding double zeros 0.65 over S. And what's happening actually, you can see that this is what I draw actually in green line. Gene yeşil çizeyim de şey olsun, aynısı olduğunu anlasın derste olmayanlar. So when you increase k, poles are moving in this way and ends up here, and also starting that -1, that's starting -5. So 2.5 is the one. You can end up with different root locus curve. Biraz küçülteceğim şimdi. Now you can see that for k, this one is zeta points almost 7. That one is zeta. I don't think that's the good one as far as oscillation is concerned. And that one is k is increasing. K13, by the way, K13, they are almost very near to zero. So that means these two effect of these two actually dominant poles are cancelled by those double zeros, which we add here, double zeros, and then we end up with this curve. When you end up with this curve, you can select whatever the k is appropriate for you. For example, K60 is terrible. You don't like it. But K30 is is a bit fast, but however, overshoot is a little too high. K13.8, which is nice. You can see that for K13.8 is already roots are already very near to zero, so it's cancelled effect of those. That's nice. For example, you can get a good uh, overshoot curves. Now I'm going to come back. That's the one with zero point 0.6 without. So you can see that the first Ziegler-Nichols method is giving us this one, 60% overshoot and almost 12 uh, second settling time. But if you look at that one, it's nice. It's 20% overshoot and the settling time is somewhere 6 seconds or something like this. But if you want to increase further, you put another value, then you are sacrificing the overshoot. Overshoot becomes 25% or something like this, but settling time becomes very fast. You can see that. For this case, I'm going to give you exact numbers now. For K13.3, K30. K30 is the better value. Evet, burada biraz dinlenelim çocuklar. Buradan bir özet alacağım. Ondan sonra da bir başka yani PID ile ilgili bir başka şey var, metot var, onu söyleyeceğim. Tamam mı? Let's take a break. Ben ama bu 14 kişiyi, şimdi 14 oldu. 13 kişiyi bir kaydedeyim. Yusuf, Mehmet, Ozan, Omar, Muhammed, Mahmud, Halil, Hamza. Hamza, we have two Hamzas. Erdem, Ali Umut, Ahmet, and Abdurrahman Efe. Evet, bir şey yapın. Kahve molası yapın. 11'i 13 çeyrek geçe. Önce şu yoklamamı kaydedeyim de. Attendance list. Çocuklar, imtihan çok yakın ha. Examination is very near. So that's why I always repeat. And final home assignments are important. Tamam. 11:15. Bekliyorum. I see you 11:15. 10:15. I'm sorry. 10:15. We have a break. Evet, yapıştırdık. Now for PID, the second method, I'm just going to review. For the second method, we obtain the oscillation point, and the oscillation point, we increase K, and when the roots are crossing j omega axis, we obtain KCR first. And then we also measure the PCR. We obtain, uh, uh, as long as you put KCR, you can see that when you put KCR, you obtain the KCR value. Then the delta is the denominator of the transfer function, and the KC, if you put KCR is equal to 30, you obtain omega. As long as you obtain omega, you also obtain the periods, PCR. When you obtain PCR, you look at, you already PID values, you already obtain KCR and PCR. So KI, TI, and TD values are defined. Those values are defined here. So either use this equation, either use that equation here, either use this equation here, that one, or use this equation. Both are the same equation, by the way. So that means we are actually adding two zeros to this system and one pole. Those zeros are defined by using first Ziegler-Nichols method. And when you solve the problem here, you can see that the zero is somewhere minus 1.4. So if you write S plus 1.4 equals 0, that means S is equal to minus 1.4. For 1 minus 1.4, double 0, and S, when you draw, of course, you can write the equation here, then you can obtain the system transfer function, and you can draw root locus curve. You can draw also step response. This is the step response. And also you can look at the root locus curve, the red one. And you realize that your curve, while you are increasing K, you are not getting any benefit. So there is no point. That zeta is almost constant. So what are you going to do? That means you are going to change the location of the double zero here. Shift the double zero near to origin. So if you assign those double zeros here, you are going to change, the red one is going to change and the green one is going to be obtained. The green one is telling you that actually these two zeros, there are two poles here as well. Cursor. There are two poles here at origin, and we are adding two zeros very near to those. So these two couples, and then you almost cancel each other. In the meantime, that minus 1 and minus 4 here, minus 1 and minus 4, sorry, minus 5 here, are free. They couple together, and they constitute similar to second degree, second order root locus curve, which is far away from origin. It's nice. And these are dominant poles, by the way. These are almost zero now, the poles here. So there are no dominant poles here. Then this, we can select whatever decay we would like to have. You can see that K value here is this or that one. This one is giving you, sorry, This one is giving you this, and that one, the second one, although its overshoot is slightly worse than the first one, but speed is even increased further. So that is what second Ziegler-Nichols method and the improvement of it is all about. I'm going to define a home assignment for you, so you are going to do it. But in the meantime, there is also a method to do this. You might also assume that dot double zero is something like this. That is completely different problem, of course. By adding double zero here uh, needs a computer program to do that. So I'm not going to give those computer program to you, but in the meantime, in the future, you might need those, so you can look at the Ogata's book, page page 5, example Ogata, example 82, page 593. In your future, if you need those, so by looking at those, you can write a computer program, and the program itself is going to define you. The program, I'm going to show you the program. Can you see this? I don't know whether you can see that. So it's a very long one. So we can't write those computer program. You can if you want, you can use it in the future engineering life, and you can see that for example, 9% overshoot is successful for that example. For this example, you have 9% overshoot is achieved. Settling time is somewhere 2.5 seconds or something like this. Even you can reduce the overshoot if you for this one A is 0.9, for that one A is 0.7. Then even the overshoot is reduced, and the speed is also reduced too. Speed is increased, that means response time is reduced too. That's it. Now I would like to come back to another point. This is a root locus. Another point is the Bode plot, Bode diagram. You are not going to be responsible for the examination. However, we also have to look at the basics of the Bode plots, particularly for those whether mechatronic engineering students are taking signals and systems course. Are you taking signals and systems course? Yes. So Abdurrahman, probably you have heard about Bode plots. In which course uh, people mentioned about body plot to you? In which course before the control? Tamam. Diğerleri, is there anyone who remembers what body plot is all about? Body diagram is all about. Okay. When you graduated, probably some of you are going to continue further education, masters. Some of you are going to join companies, industry. So if you know nothing about body plot, that is going to be a very negative starting for you. So therefore, although I'm not going to ask any examination question, but that is also important, and I'm sure I'm going to give you fundamentals of it. Fundamentals. It's very important. You see what's happening actually. What's happening? The That is the control problem, or this one is the control problem. This that one that this one is our system. Okay, so S in steady state case with frequency is changing from 0 to infinite. Don't forget, I repeat, your frequency is changing from 0 to infinite. So sinusoidal case, you have a sinusoidal input. So what is your response to sinusoidal? Of course, for electric circuit people, you already know what impedance is all about, what is the current, what is the voltage, and what is the uh, angle between current and voltage. You already know that, and you are going to while you are going to learn when you take power electronics course from me, I'm going to also emphasize the sinusoidal responses too for power electronic concept too. So however you should now learn, I'm sure you are going to combine the knowledge you have got from circuits, from signals and systems. It's going to be open up your mind. All right. So what S domain is actually is it has S has got a real component and imaginary component. But for body plot, we assume that your input signal is sinusoidal. Therefore, you are not going to take any real part into account. All right. So I'm going to open up. Never ignore my home assignment. Okay. I'm going to give you home assignment for PID, second Ziegler-Nichols method. Never. It's a 10 point, and also it's going to also help you to become successful in the examination. what we are going to do, S equal j omega. Analysis and design of control systems by frequency response method. Now we have time function here, time function there, input, and we have time function output. But in S domain, we convert it to time to S domain, and then output in we are going to obtain S domain as well. And we know how to come back to time domain as well. That is a general representation. If you have a sinusoidal input like this one, x sine omega t, and the y output might be sine omega t plus or minus phi. Burada plus vermiş ama it might be plus or minus. For example, if you have a voltage for example, that means your voltage in phasor the angle is 0, but the amplitude is Vm. So this is the complex representation of this one. If your impedance in a circuit, I'm explaining in a circuit. This is a reference, but that one sinusoidal input, and that is the circuit. Okay, so you have an impedance Z. Assume that, biraz incelteyim bunu, çok kalın gidiyor. Inductance, for example, Z is equal R plus J omega. Inductance. I'm sorry. L R times of load. If it is so, current complex is equal V complex over Z complex. In other words, V RMS or maximum value, RMS yazayım. V RMS 0 over Z phi. Bu Z phi nasıl bulunacak? Since Z is equal R plus J omega, which is equal to evet Ali Umut, doğru. Bu nedir? R square plus omega L square over phi. Phi is arc tangent omega L over L. So that means I is going to be Vrms over Z amplitude minus phi. Okay? So that's why that logging means that this one is that current is logging actually. That one is the reference, voltage is the reference, voltage is the reference waveform, and the current is the logging. However, if your impedance is R minus j omega, that means capacitive, then current leads. That becomes positive. Leading and lagging concept is coming from that one as well for our control lead lag compensation. So this is just starting. Your input is sinusoidal and your output is sinusoidal too. But what you are going to do in your control problem, as long as you saw S, you are going to replace it with j omega. Okay, so S in our body system, we are going to put S is equal j omega, which is obtained. This is a first order system. And since I come back, since omega is varying, from 0 to infinite, so we have number of omega values. Omega equals 0, omega, let's say omega n, somewhere there, resonance value, and omega equal infinite. So we have infinite values. In order to cover those, logarithmic scale is used. For logarithmic scale, the conversion table between decibel values and the numbers, the horizontal line numbers and vertical line decibels. You can see if you concentrate on the horizontal line, you can see that this is from that one is 100. Between that point and that point is 100. Between that point and that point is another 100. 100 mı? Bir dakika. Bir dakika. 10. 10. 100. 1000. Tamam. Şimdi oldu. Yanlış söyledim. Burada between that point and that point is 10. Between that point and that point is another 10. And between that point and that point is another 10. So 1000, bakın 1000 sayısı burada. We have 1000 here. But in the meantime, the decibel numbers are changing from minus 40 to plus 20. And that, you can see that point here. Logarithm of 1 is equal to 0. Logarithm of 1 is equal to 0. So 20 logarithm of k is equal minus 20 logarithm of 1 over k. One rule, this one. And k times 10 is equal 20 log k plus 20. Bunları unutmayayım diye yazdım. Ezberlemenize gerek yok. Şimdi bode plot nasıl çiziliyor onu göstereceğim. If you have a curve like this, 1 over j omega, this one is 1 over s. Değil mi? Bunun karşılığı aslında 1 over s. Yani bu, if you look at that one, gs is equal 1 over s. That one, gs is equal s. For that one, the logarithmic curve is starting from 20 to 100. That's constant line. J omega line in Bode plot is a constant line. However, the slope is constant too. You can see that the slope eğimi is constant too. And for that point is important. Uh, Omega equal in horizontal axis is omega, and the vertical axis is decibel values of the logarithmic scale. So for omega equal 1, since it's equal to 0, and for this one again omega equal 1 is equal to 0. This is starting from minus 20 is positive, that is starting from plus 20 negative, and final value is 100. You can see that, sorry, 400 is 40. Now for what about that one? Who is going to answer this one? Bunun angle'ı sabit. Bakmayın şekle. Bu paydada olduğuna göre bu angle kaç derecedir? Yani is it positive or negative? Paydada olduğuna göre iki tarafı da j ile çarpın. J kare gelir buraya. Yukarı j çıkar. J de 90 derecedir ama j kareden eksi geldiği için eksi 90 derece. Teşekkür ederim Ali Umut. Negatif doğru ve 90 degree. Angle is 90 degree. Angle of this one is 90 degree. C biliyorsunuz şey demek. 90 derece demek aynı zamanda. E üzeri G pi bölü 2. Bir dakika ya, pi bölü 2 mi pi mi ya? O zaman yanlış yazmış da olabilirim o şeyi. Neyse kontrol ederiz. Devam edelim. Şimdi bu 90 derece eksi 90. Bu da artı 90. Tamam mı? Açılar, but angle is constant. Şimdi gelelim böyle bir grafiğe. First order. 1 plus bunun aslında S domain karşılığı GS is equal to TS plus 1. First order system. So that means S equal J omega. The curve is something like this. For small values of omega is for small values of omega, the logarithmic response changing like this. I remember we used to draw those curves by hand, by the way. Now I'm going to show you. Computer is going to draw. Don't worry about how could I draw those curves. Computer is going to draw your curves. Anyway, so your amplitude of your system, of your transfer function is almost zero for small values omega. Çünkü 1 oluyor. Logaritma 1'de 0'dır biliyorsunuz. So then it deviates when the omega is equal 1 over t. Omega equal 1 over t ne demek? Buraya j 1 oldu demek. Sonra değil mi? Omega 1 over t ise t'ler götürür. J kalır. 1 plus j'ye dönüştü. 1 plus c'ye geldiği zaman zaten açı 45 derece oldu. Angle. And the amplitude goes down. And when omega increases, it goes down and becomes a negative value. Amplitude. If you look at the angle, if omega equals 0, angle is 0, then deviates from 0, and that point, corner frequency is called, that omega is equal 1 over t. Sometimes I call it resonant frequency as well. Then this of course there's no resonant here. It's a first order system, and then this point angle becomes 45 degree and end up with minus 0 from 0 to minus 90. Yani omega infinite olursa zaten bu one neglected, o zaman da eksi 90'a geliyor. Bir önceki 1 bölü j'ye yaklaşıyor. Eksi 90 da hatırlarsanız her zaman. Şimdi esas bir plus olursa ne olacak? Bu minus'tı. Değil mi? Bu minus'tı. Aşağıdaydı. Plus olursa, yukarıda olursa 1 over j omega t olursa, o zaman da yine sıfırdan başlıyor. Logarithm of 1 is 0. If omega is 0, it's logarithm of 1. Then it's going to start 0. But then this is the 1 over t corner point, and then amplitude goes up. And also this one is the angle. Angle becomes positive 90 then. It was negative 90 for the just a moment çocuklar, bir saniye. Kusura bakmayın. Geldim. Evet. Şimdi if omega goes to infinite, that one is minus 90. For GS equal 1 plus j omega t, omega goes to infinite, angle theta diyeyim hadi şöyle, eşittir plus 90. Tamam mı? Bu da theta eşittir minus 90. Okay. So these are the first order systems. Şimdi second order sisteme geleceğiz. Bir overshoot. Şimdi bakın second order system. Bunun karşılığı S domain karşılığı nereye yazayım? Şuraya sığdırabilirim herhalde. Omega n square over S square plus 2 zeta S omega n plus omega n square. Bunu hatırlıyorsunuz hepiniz. You remember that one. So bu bunun karşılığı. So transfer function is equal to, follow my arrow, 1 plus 2 zeta j omega over omega n plus 1 plus j omega over omega n square. So S is equal j omega. So we replaced with j omega. Okay. So you divide it by omega n square. Therefore, the numerator is 1. Neyse ki, you are not going to draw those curves. I'm going to amplify it. The body plot, the MATLAB is going to draw your curve, and it's going to be giving you those curves. For zeta, you can see that for zeta 1, which is, you remember that it is overdamped case. For zeta 0.7, somewhere there, 0.7, and zeta 0.5 is here, and then you can see that the 0.01 is very high increase in logarithmic scale. The decibel value is increased, and also the amplitude of this one, when omega goes to infinite, it becomes minus value. For angle, however, that is the corner point. You can see that omega is equal 1 over t. Sorry, omega is equal, omega over omega n is equal 1. That means omega is equal omega n. That angle becomes 90 degree, but it starts from 0 to minus 180 degree. So angle is varying, and the curve is something like this. Probably you may wonder, why are you going to use that one? Body plot is particularly used when the frequency response of a system is required. So what, for example, resonance systems, for mechanical engineering students as well, it's going to be used. But mainly in electronic circuits, we design filters, we design other systems and control systems. We would like to see the system response with respect to the change of the frequency from 0 to infinite. And that picture is telling you, and you can see the overshoots easily. That one is the also telling you the maximum overshoot relationship with, of course, in decibel in that case. Maximum overshoot in decibel with zeta. Bu problemi bakalım nasıl yapacağız. Şimdi C omega, şimdi bir dakika bir geri dönüyorum başa. Ben nesiniz değil mi çocuklar? Basit bakın, iş basit. What we did actually, we replace S equal J omega. And omega changing from 0 to infinite. And since it's a number of points are too much, we use logarithmic scale. For logarithmic relationship, every 10 point is represented like this. And the decibel values and the number values relationship is something like this. And we have already seen that if the function is like this, the amplitude and angle. If function like that, amplitude and angle. If function instead of that, this one, which is a first order system, the amplitude is something like this, angle is something like that. And of course, in positive one, that one here, its amplitude is getting up and the angle is starting from 0 to 90. However, for second order, typical second order response of the transfer function like this, it is the plot depends upon the zeta value, and you can see the overshoot, and that one is actually corner point is called omega, is omega n, and the angle here is minus 90 degree, but varies from 0 to minus 180 degree. That is the amplitude relationship. Now this problem, this one is constant. Yalnız beni iyi takip edin çocuklar. That one is constant. That one is j omega minus 1. That one here is plus. This one there is this one minus in denominator, and this one is second order. So we have already studied each response of it. So those curves, bakın bir numara 7,5. Nerede o? Heh. First one is here, constant. 7,5. 2 numara j omega minus 1. Nerede o? 2 numara. Bakın 0 gidiyor, yükseliyor. Nerede o? Pardon. Şu. 2 numara. Tabii sabit. Bunlar amplitude'lar. 3 numara şu. 0 gidiyor, goes 0, then for the corner point it goes up. Bu da 0 gidecek ama 4 numara aşağı inecek. Going down. Nerede o? 4 numara bakın. Geliyor 0 geliyor, sonra 4 aşağı iniyor. 5 numara malum şu oscillation. Şu 5 numara. Şimdi bunlar 5'i nerede göstermiş? Evet burada. Şu. Bakın. Şöyle geliyor. Angle'ları da her birinin angle'ını ayrı ayrı gösteriyor. 1 numaranın angle'ı constant. 0. 2 numaranın angle'ı o da eksi 90'da constant. We have already seen that. 3 numara angle'ı tabii ki yukarı doğru gidiyor. 0'dan 90'a doğru gidiyor. Bu that one from 0 to minus 90. Nerede o? Kaç numara bu? 1, 2, 3, 4. Fourth one. Yani minus 90'ye gidiyor. 5 de bu. minus 90'den minus 270'ye gidiyor. Bir dakika, 5 numaranın açısına iyi bakmamışız burada demek ki biz. 180 ya 5 numara. Sıfırdan 180. Bir daha bakayım burada. Ha, 5 numara burada çocuklar. 5 numara. Sıfırdan 180'e gidiyor. Tamam. Hepsi beraber all together is going to be something like this. Şimdi bu ne işe yarıyor? Bu Bode plot ile while you are using Bode plots, you can design control systems. But I'm not going to spend time on it. You can pole zero, for example, that one, for example. Is this one lead or lag? If that one is near to origin, is lag network, that one. This one is completely different, but I'm not going to give it. There is one problem, for example, solved for L and T is obtained and solved. This is the problem. Probably first Ziegler-Nichols is applied here. Buralara girmeyeceğim. Biraz yürüyeceğim çocuklar. Şimdi bize lazım olan ne? How do I draw Bode plot? If you know the transfer function, all you have to do to write Bode num den or Bode num den W. If it is a state space, which I'm not emphasized on this one, Bode ABCD or Bode ABCD omega or Bode system. Magnitude could be obtained or converted to decibels. So these are the definitions. If you need, you can use it. Now bir problem. Bunu ben yapıştırdım üstüne. Biraz büyük görelim diye. System has got 25 s square plus 4s plus 25. So omega n square is 25. So omega n is 5. So zeta bilmem buluruz. Bulunur yani. What are you going to do? You are going to write. Buraya dikkat edin çocuklar. Bu işinize yarayan kısım. Num equal 25. Then 1 4 of course space var arasında. Space 4 space 25 dot comma. Then if you write Bode num then it's going to give you the curve like this. So you can draw Bode curves. Don't feel that you are not capable to do that. All you have to do, so far you learn the transfer function. As long as you write, you obtain the function, for example. This may not be transfer function. This may be a system function as well. For this system, you can draw the Bode plot. So you can see that the Bode plot is changing like this, and the angle is changing like this. Şimdi one thing you should learn. I'm not going to try to teach all the details of the design of control system with Bode plots. We have no time. However, one thing you should learn. What is gain margin? What is phase margin? Gain margin And phase margin is telling you that if that one is positive and that one is positive, your system is stable. So also stability analysis could be done with phase margin and gate margin. Ah, ben siliyorum o kalem böyle uzaktan yazma moduna girdi mi yanıyoruz. Unutuyorum da sonra. Bir kere vursam şeye böyle o zaman vazgeçiyor. For stability, that gain margin and phase margin. Şimdi gain margin is something like this. Look at that one, that point. And also look at that point. This point, which our gain function crossing zero, and then this point, when you fix this point, come to this point and obtain the angle. If angle is how many degree is away from 100 minus 180 degree, it is phase margin. Okay, and if your angle plot cross minus 180 degree, obtain that point and then move to the gain, and this one is gain margin from first. I repeat, listen carefully. Only few things you are going to learn. You know, Bode plot is something that frequency changes from 0 to infinite. That's why we represent our system uh, amplitude and angle in logarithmic scales. The amplitude is telling us how much our impedance is changing actually. Or if you obtain the transfer function, of course, your model system represented. And the amplitude uh, would be drawn by MATLAB by writing num then and then uh, bode num then. That's all right. So you can get those curves. Now, if you look at those curves, you are going to obtain where your gain function is crossing zero. As long as you obtain that point, you come to the angle curve and you obtain the point how far it is from 180 degree. You can see that 180 degree. So that one is your phase margin. Phase margin means that you are how comfortable you are from the stability limit. If if these are changing the sign, your system becomes unstable. For k equal 100, k equal 10, the same function, k equal 10, you can see that system, the gain margin is positive. That's the obtained the crossing point 180, and then you look at the curve, how far your curve is from zero. Be careful, bakın bu eksi 10 olmasına rağmen bu artı diyor. Yani buraya doğru artımız var. Bu kadarlık yerimiz var. So it's a gain margin. So gain margin is positive, phase margin is positive, system is stable. However, here for 100, gain margin is negative and the phase margin is negative too. System is unstable. Şimdi ne öğrendik peki? O zaman we have learned, bunu hatırlıyorsunuz. We solved that problem. We solved that problem with second Ziegler-Nichols method. And galiba bunu da second Ziegler-Nichols metotla çözmüş. Bu başka bir example. Daha fazla uzatmayayım artık. Yani hemen gain marjinları ve phase marjinları işaret etmiş, dikkat ederseniz. Evet, bir de bunu başka bir derste öğrenmişsinizdir. You already learned that one. It's if your gain reduces below -3, then the area inside that one is called bandwidth. Bandwidth. Bu kadar yeter. So we have just reviewed how could we draw what is body plot is all about, and how could we draw the body plots. And also we can design our control system by using body plots, which I haven't given enough emphasis on this one. However, you can continue if you want in your engineering life. The phase margin and gain margin are important parameters for the body plots. Well, şimdi çocuklar, bundan sonra bir genel tekrar yapacağım. Bugün son dersimiz. Genel bir tekrar yapacağım. Bütün slaytları birer birer şöyle gözden geçireceğim. Sizin aklınız fikriniz sınavdadır. Onu da söyleyeyim. Evet. Yani sorular hazırlanmadan ne olduğunu bilemeyiz. Ama şu son verdiğim ödevi, şimdi bir tane de şeyden vereceğim, PID'den ödev vereceğim. Son verdiğim ödevi muhakkak yapın. Yani şeyi de lead compensator'ı da öğrenmişsinizdir. Lag compensator'dan ödev vermedim ama o da kolay. Bunları öğrenmişsinizdir. Şimdi bir ilk güne bir dönelim bakalım. Birinci hafta buna başlamışız. Gain demişiz. Bunlar size artık peynir ekmek. Also, how could we understand whether it's good or not? Of course, we have to add an actuator to this system. Process, actuator, controller. This is open loop. This is a closed loop system. If you add a sensor here, the transfer function of the sensor also involves that one. And we all know the obtained transfer function. These are control systems. This is a disk-derived position control system where we also emphasize that it could be a rotational or linear motion. And I also give an example of the hybrid electric vehicle through the front axle is driven by internal combustion engine, and the rear wheel is driven by the and also this one is very now it's very hot topic. You all know that we are working on autonomous drives for many years. Now we are developing a library for autonomous vehicle developers in our university. Our university is selected as a top on this topic by European Union. So European Union allocated some money to our university, to our lab. But however, for the control problem here, so you have to detect the curvature of the road, and then you are going to change the steering wheel. If it is a robot is sometimes called robot taxi, then robot is going to decide which direction it should go. It's a good control problem. And also manufacturing process and linearity we talked about. We although that curve is a linear line, but in mathematical wise, in control wise, we cannot assume that it's a linearity condition. For linearity condition, y is equal to ax. If system is linear, we employ the superposition theorem. We know that if you have multiple inputs, and then if you want to get total output, you can employ each of the inputs. Linear time invariant and time varying systems, we generally solve our control problems with linear time invariant systems. These are the functions we give, input functions. It could be step, ramp, parabolic. That also reflects the position. That one reflects the speed. Parabolic reflects the acceleration. Of course, it could be a sinusoidal. We discussed the body plot for this one. Yeah, these are the utopic objectives. Steady state error should be 0. Transient, the settling time should be 0. It is not possible, of course. And overshoot should be 0. And also cost should be as low as possible. Inner loop, outer loop. First, you are going to solve the inner loop. You are going to solve the inner loop first, then the outer loop. We have two approaches. One of them is transfer function approach. The other one is state space approach. State space approach uses time domain in matrix forms. We haven't emphasized much on this one, since you have to learn first the basics of the control, which is based upon the Laplace transforms. These are the functions. If it is a step function, is 1 over s. If it is a ramp function, is 1 over s squared. If it is a parabolic function, is 1 over s power to 3. Exponential function, 1 over s plus alpha. Sinusoidal function is something like this. I also have given you theorems, the translated function, multiplication function, real differentiation theorem, final value theorem. This is what we use our steady state error calculation. Initial value, convolution is a multiplication of two functions actually, product of two time functions, and partial fraction expansion method. We also worked on this one. I have picked Professor Rice's book and put it in our list, and I have some problems put it here. Then we moved second. So we realized that system most likely is going to be the mechanical or electromechanical. So we have to model those properly. So if it's a rotating system, but don't forget, we are not talking about disk. We are talking about, look at me please. We are talking about the arm. This arm. This arm. This arm is rotated by electric motor, and the equation here, the inertia always reduce the starting point. Since it requires to store energy inside it, but that one is loss, friction, and that one is also energy storage. So I'm sorry, this is load. Buraya bir hemen şeyi de ekleyeyim oraya. K theta, bu da spring constant. So it's actually uh, uh, represent the stored energy, of course, for the spring action. Siz benim elimi göremiyorsunuz. Ben buradan şimdi kendimi görünce fark ettim. For the spring action. Evet. So we have, this is a rotational system. That one is translational system. In that case, the mass is the energy storing system. Although it is difficult to accelerate the system, but also it is difficult to decelerate the system as well. Hızlandırmak da zor, yavaşlatmak da zor. B is the friction again, is a loss, and the K, for example, if you use a rubber material, for example, they also store energy, and also F load. If there is a load, you have to satisfy those with your electric machine. Single input, single output, multiple input, multiple output. So these are simple. The transfer function we obtained. We already solved several problems on it. Closed loop transfer function, GS over 1 plus GSHS. And serial, parallel, and also feedback examples. Again, that figure probably the summary of my course. You have your reference input, and this is your output, and this part is the controller part. So mainly this amplifier is a power electronic network. You are controlling it, but that one is error, actually actuating error signal. And also we have seen that proportional controller, integral controller, PI controller, PD controller, and PID controller. Salı günü imtihana giriyorsunuz çocuklar. Yani ben bile heyecanlanıyorum, biliyor musun? Yani bu kadar, bir hafta sonra imtihana giriyorsunuz ya. Vay canına. Bu kadar, yani canım sıkılıyor. Yani üniversite hiç değilse bir hafta ara verseydi iyiydi. Ama işte onun için form tutmaya çalışıyorum ben de sizinle beraber. Sizin formunuzu artırmaya çalışıyorum. Kontrol, on-off kontrol, yani bizim evde de var mesela. Termostat var. Kaloriferleri 22'ye gelince yakıyor. Ondan sonra ama 22'nin biraz altına düştüğünde kapatıyor falan. Evimi de güneş vuruyor mesela eve ön taraftan. Termostatın olduğu taraf sıcak. Başka yerler yani on-off kontrol iyi bir kontrol değil özetle. Ben şikayetçi değilim hani gayet iyi çalışıyor sistem filan ama e, az, tabii yani bütün ısıtma hemen hemen tüm millet on-off kontroldür. On-off kontrolda bir maksimum bir de minimum arasında değişiyor. Between maximum and minimum. Maximum'a geldiği zaman 10, then of course there is a gap. There is a gap between those. Mesela bizde tahmin ediyorum yani 22'de çalışıyor ama yani 20 belki de 22,5-23'e doğru kesiliyor. Fakat aşağıda da yani 21'e kadar indiğinde 21'de belki çalışıyor. Yani 21 ile 20, şimdi 22 ayarlıyorsun ama belki de o 21 ile 23 arasında. I'm sorry for Turkish. Probably between 21 and 23 fix it. Bu çizdik bu grafikleri, hepsinin denklemlerini yazdık filan. Ondan sonra proportional controller. Artık bunlar size peynir ekmek. PID yaptık çünkü. Integral controller. Ama şurada şu resmi unutmayın ya. Şu resme tekrar bir geri döneceğim. Çok yani önem verdiğim bir resim. Bakın bu yani burası controller diyelim buraya. Controller çıkışında U var. Tamam mı? Girişi E, çıkışı U. Sorry about that. Just a moment. Integral controller and also proportional integral, proportional derivative, proportional integral derivative. At the end, we add two zeros on pole. This is what PID is all about. That's the one. If you have a disturbance like this, what are we going to do? We are going to assume that there is no disturbance. We are going to obtain one output. Then we are going to cancel that one. And then only disturbance we have obtained another output. Therefore, two outputs together is the final output. Of course, we are not happy about disturbance. In order to reduce the disturbance effect, that G1 and HS are all control. HS generally not, since it's a sensor, but G1 is controlled to do that. We have already solved those problems. You remember that? Derive steady state error when both the reference input RS and disturbance input are present. Of course, I haven't told you these are whether these are step or ramp, whatever it is. I haven't given you here. Oh yes, we also know how could we derive uh, if you know the electronic circuit, how could we derive the control network of it? Of course, this is 1 over R. This is integral 1 over C integral I dt, which is equal. Integral means 1 over S. Derivative means S. So bunu da tekrar etmiş olduk. So reduction, if you are going to reduce that one, you shift that point to this point. But while you are doing that, of course, you have to consider that you have to divide. These type of systems were very popular in the past, but now I think the computational methods are decisive. You can see that we are now shifting that one to this point. But in the meantime, we are dividing by G1 since it's going to be multiplied with G1 anyway. Okay, so first solve this one, then solve that one. It's a feedback, another feedback, and then obtain the final result. Time domain state space method we discussed briefly. I have no intention to ask any question about it, but this is also important topic in for advanced control. For example, if you take another course, advanced control course, it's all based upon the state space. A is a state matrix, X is the state variable, input matrix, output matrix, direct transmission matrix. We also derive those equations in, so this is a typical differential equation, and we define x1 is the state variable y, x2 is y dot. Therefore, as a result, you end up with the first order, since you can see that these are first order differentiation occurs here. First derivative, I'm sorry, first derivative. And output that one. It's time domain. Solutions are in time domain. And you can see that x2 dot and y is equal output can be obtained. Bunu yazanlar oldu sınav kağıdına ya. Enteresan. İstenmedi ki. Neyse yürüyelim bakalım. Bunu istemiyorum. Söylemiştim. Third week, it's a combination between Hoft Bishop's advanced control and Ogata, your reference book. So the spring action, we talked about that one, and also the that is the point. Electric quantities, mechanical quantities, thermal quantities, hydraulic quantities, the equations are similar. Therefore, there is a similarity between those. So I emphasize that one. I'm not going to give in detail. And we also solve that problem. There are those equations. We also have solved that problem, and we have looked at the similarities between mechanical system and an electrical system like this. Almost same equations. These are, that one, for example, is diminishing, so it's a probably impulse response. Constant current source, that's right. Linearity, the two theoretical point is important in control. One of them is linearity, the other one is sensitivity. Sensitivity problem is something, if your system is robust means dayanıklı. If your system is robust, that means it is less sensitive to parameter variations. Bu da linearity. So if system is nonlinear, so we assume that in one point you can make it linear. Burada bitmiş. Yok, bitmemiş. Bir ek var. Boş bir sayfa koymuşum bir şey yaparım diye. Of course, Laplace transformation tables are important, as well as to come back to electric machine model we developed Probably you have completed electromechanical energy conversion course today, I mean, this week. So you uh, mix the knowledge you have got from um, uh, electromechanical energy conversion and make electric machine together. That is the model. This is the typical electric machine model. That one I don't like it since the field is not used anymore. We use permanent magnets instead of those, and that's more realistic model of the electric machine. This is the armature winding of the electric machine. This is the mechanical part of it, and of course that one is a speed error. That one, or this is output is speed, but then if you multiply with uh, 1 over s, that means you are integrating the speed, you get the position as well. But this one is a speed control electric machine system. Of course, for today, for electric vehicles, plenty of electric vehicles now on the road, they all use this control system. They control the speed. Operational amplifiers are important, but you don't have to memorize those. Just input-output relationship is the transfer function of the operational amplifier, and these are, for example, integrate. That one is derivation. You multiply with s, and that one is also derivation, differentiation. So get the derivation of it. This one is differentiation in another circuit. That one here integrating that one, since s is in the denominator. So these are the models. Gear, for example, in your engineering life, you might face with gear systems. That is, for example, still used in uh, steering system of the vehicles. Direksiyon sistemi bu prensiple çalışır. Yani sen direksiyonu çevirirsin ama şu tekerleğe giden şey lineer hareket yapar. It moves in a linear motion. Kenarından tekerleği iter. I asked the examination question for you. Typical electric machine control system. And step response, for example, this is a nice step response, by the way. You can see that settling time is 0.6, even 0.5 settling time. And the overshoot is çok düşük. Yani çok güzel. Neyse devam edelim bakalım. Fifth week was one of the fifth week course or fifth course, one of the major points, the first order system response, that's the one. And of course, error, unit ramp response error here. can be seen. And the those I solved that one, and we obtained that time goes to infinite. Steady state error remains t here. Burada output. Time s goes to zero. Neyse uzatmayayım. Bunları biliyorsunuz. You already know those. Unit impulse response for the first order system. But second order system is our main task. You are familiar with that equation here. You are familiar with it. These are the at that this is the characteristic equation. That is the transfer function. That's the characteristic equation, and the roots of those are your decisive, giving you information about your step response, ramp response, and things like this. And sigma is the attenuation is the real part of the poles. These are the real part. Omega n is undamped natural frequency. Zeta is damping ratio. Omega d is damped natural frequency. Of course, we have underdamped, critically damped, overdamped, undamped. Undamped means sinusoidal. Overdamped is excessively damped. There are two poles real. That one critically damped, two poles are equal. And underdamped is the generally what we deal with cases. And also the relationship between those, omega d, that's a pole, and sigma. Sigma is important. If sigma is high, settling time is getting down. Good. Zeta, of course, beta is giving us the zeta value. Cosine beta is equal to zeta. Typical step response, we all know that. The maximum overshoot, rise time, settling time. And this is a typical mechanical system response. We studied that one too. And we have seen the effect of the sensors K, KP as well. KH, I'm sorry. Bu kadar yeter burası. These are the poles located here, poles located there, poles located here. They're all stable. But here, j omega axis, poles are, of course, if it gets down, frequencies down, gets up, frequencies higher. However, these are unstable. For those, there is no oscillation, but unstable. For those, there is no oscillation, but of course, that speed is higher. For this one, speed is lower for that one. Speed is lower means that these are dominant poles. Poles near to j omega axis are called dominant poles. If you have a transient response for higher order systems, we already discussed that one. That's the end of the. We start with state space. I'm not going to spend time on this one. Yeah. Bunu yazın demişim. State space'te yazın demişim ama yaptınız mı bilmiyorum. Ödev olarak vermedim çünkü. Correlation between transfer function and state space we have not spent on time much time on this. Transient response analysis with MATLAB, we are already familiar with that one. We have curves like this with MATLAB. You can easily stability. We studied Raut-Hurwitz method. Here we solve a problem. We have seen some critical points as well. So the first column you write and then multiply with this one, 1 to 2 minus 24 divided 1 is minus 22. Any change in the sign is giving you how many poles in the right hand side. That means stable. It's not stable. These are feedback, sorry, MATLAB statements. PID, proportional controller, error, K over S affect that one, and also KP effect of this one, how your disturbance, error of the disturbance is affected by KP. KP is actually reducing the disturbance. And also adding a integral makes it 0. So adding integral is even getting much better. These are the typical systems. We evaluate those. And that one is oscillating. If you, however, add a derivative to this one, it controls this one and system becomes stable. The derivative controller effect is given here. Bakın bir 7. chapter'ı açtım. Bakın böyle bir sınav sorusu sormuşum şeylere. Midterm'de öğrencilere. Bundan sonra bu da diğeri sormuşum. Bu 3. sorusu. Bu da 4. Demek ki MATLAB statement'ları falan da vermişim. Kolaylık olsun diye. Steady state error'da çocuklar yani type important. Steady state error you already know how to calculate, but type is giving you some easy solution. For of course steady state error is this one, and if you look at the steady state error calculation for static position error, it's called KP. KP should be high. Static position error. Bakın. Yani theta veyahut x. That is static velocity error. KV. KV should be high. KV should be high. And also we have a table. And static acceleration error. Bu da ivme hatası. Orada da Kp should be high. Tabii your system type 2 is necessary. If it is type 0 and time 1 system, zaten error is infinite. That is the table for K values. Bitti. Şimdi bir tane daha var. Artık son konulara geldik. Sekizinci hafta, hatta 8. lecture diyelim. Tamamen root locus. Root locus'u çok uğraştık. Artık uzatmayacağım fazla. Root locus bir iki resim gösterip gideceğim bu root locus'tan. Çünkü şeyde de kullandık root locus'u. Ama we have proved that the transfer function roots are moving with k. K0 means that it's the poles of the G or GH, and K infinite is the zeros of the J. Uzatmayayım. Mesela bu second order system. Gördüğünüz gibi hep lineer. Sorry, hep stable. Polun biri burada, diğeri burada. These two poles are constituted, and when you increase the K, you are going to obtain the roots are located here. However, for this one, we have three poles. It's one pole is located here, the other pole is located here. These two couples, and then this is one which hasn't got any further effect on this one, far away from origin. There are several. MATLAB is going to draw those anyway, and these are the cases where the poles are located, the trajectory of the root locus curves. Burada hemen bir sonrakinde bunu tekrar ederek başlıyorum. Çünkü design yapacağız. The last one, we start with ninth, tekrar yaparak başlıyor. Bilerek öyle hazırlamıştım. Cancellation of poles and zeros. Zaten lead compensator'da da onu yapacağız. Bu bakın bunlar zeta constant doğruları. Yani bunlar da omega grafikleri. Şimdi evet, lead compensator zero'nun etkisini görüyorsunuz. Sola çeker grafiği. Lead compensator'ı daha yeni tekrar ettim. That one is lead. That one is lag. Sabah. And also PID controller'da da KID bakacağız. Lead compensator'da ödevi de yaptıysanız eğer bundan hiç mutlu değiliz. Dolayısıyla da şu pole'dan we are not happy about that pole. Azaltsak da fark etmez. Sigma eksi 0.5 olduğu için settling time is too long. İyi değil. Peki ne yapacağız? Beğenmediğimiz polun üstüne bir zero atacağız benim metotta. İkinci metot. Bakın beğenmediğiniz polun üstüne bir zero attık. Ondan sonra öbür polda açılardan bakaraktan bulduk. Bu yazdığımız zaten çözüm gelir. grafikte düzelir. Lag'da ise bu sefer de transient'ten mutlu değilsen bu sefer de lag yapıyorsun. Bu da lag. Evet. Grafiği değiştirmiyor. Fakat steady state error'ı çok azaltıyor. Lag'da sıfıra çok yakın, daha doğrusu orijine çok yakın bir pol atıyorsun. Neredeyse orijinde. Bir tane de zero'yu hemen onun yanına atıyorsun ki bir açı farkı meydana getirmesin. Grafik aynı kalsın. Yani şu iki grafiğin aynı kalmasının sebebi the reason why these two curves are not changing is because we added pole and zero almost near. So it's one actually. Yani S plus 1 over t over S plus 1 over beta t'de ikisi birbirine hemen hemen aynı. Ama Ç'ye sıfıra çok yakınlar. Tabii pol sıfıra daha yakın. Çünkü lag. Evet, uzatmayayım burayı da. Burada yaptık bayağı bir iş. Son olarak da PID'yi göstereceğim. Ve oradan sonra da vedalaşacağız. Bakayım. Seyit gelmiş. Merhaba Seyit. Tekrar yapıyorum. Aşağı
Merhaba
yukarı
hocam.
son bir saattir bütün slaytları ve hatta 45 dakikadır bütün slaytları gözden geçiriyoruz. Bode'ye istediğim zamanı ayıramadım. Ama hiç değilse nasıl bode çizeceklerini falan gösterdim. Ve de yani gain margin, phase margin, e, stabilite ile ilişkisi falan onlardan bahsedebildim. Fonksiyonların bode şeylerini öğrendiler. Daha sonra ben anlattım da yani onların öğrenmesi için mutlaka karşılarına bir problem çıkması lazım. Ben özellikle bizim çocukların şu şeyini istiyorum. Yani yarın öbür gün bir kontrol problemi karşılaştıkları zaman yanlarında başka meslektaşlar olacak. Onlardan birisi ya bir de şunun bode plotuna bak dediği zaman böyle yabancılaşmasınlar. O zaman da hocam bir dakika deyip şöyle bir gözden geçirip ondan sonra ertesi gün bode plotlarını çizmiş olarak MATLAB'de gidebilsinler istiyorum. Neyse son sözlerim şimdi son slayta geldik. These are my last twelve. Neredesin 12? Ha, burada. PID, we have three parameters. It's difficult to obtain the starting point from zero to infinite. From zero'dan kasıt point 0.0001 for example. So infinite numbers. So we are going to use the either first Ziegler-Nichols method, that one, L and T, and look at the table here, obtain Kp, Ti, and Td, or if there is an oscillation, we use second Ziegler-Nichols method. For second Ziegler-Nichols method, we have to improve our K, we have to increase our K up to the point where the poles are located on J omega axis, where continuous oscillation starts, all right? Then, of course, you obtain KCR. Then when you obtain the oscillation, you also obtain the frequency. When you obtain the frequency, you can come to the period. As long as you obtain KCR and periods. Neredeyim ya? Bir dakika karıştırmışım bayağı buraları. Anlatırken tabii canım. Burada bayağı zaman harcadık. Yeah, that's right. When you obtain KCR and PCR, then PID parameters, initial PID parameters are obtained. When you obtain the initial parameters, of course, Seyit şunu bir kontrol etsene. Bu E üzeri J pi sinüs pi miydi yoksa pi kosinüs pi miydi ya? Trigonometri şeyinden bir Google'dan girersen hemen söyler. Veyahut çocuklar siz bir kontrol edin. Herhalde böyle olması lazım. Tabii sinüs pi sıfır olduğuna göre kosinüs pi de 1 olduğuna göre bir dakika kosinüs pi eksi 1 mi oluyor yoksa? Tabii eksi 1 oluyor. Teşekkür ederim. Şimdi aslında doğru tabii bu ama şuraya bir eksi koyacağım şimdi. Şuraya bir eksi 1 koyacağım. Heh, olmadı. Renk yanlış renkmiş. Seyit sen bugün ne yapacaksın çocuklara? Ne yapacak? Ne anlatacaksın?
Hocam bot plot diyagramı çizeriz. Bir de
Ha,
geçmişten biraz genel şey yaparız.
tamam.
Tekrar gibi.
Yani bir kere bütün step response'ları biliyorlar. Ondan sonra ramp response'ları falan biliyorlar değil mi?
Hı hı.
Root locus'ları çizebiliyorlar.
Evet, onlar da.
O zaman bir iki tane body plot çizersen memnun olurum hakikaten.
Tabii
E,
hocam.
bir dakika şu eksiği bir koyayım şuraya da. Eksi 1. Dolayısıyla da tabii o zaman ne oluyor bu ya? Bir dakika bir arkadaşınız bir şey yazdı ona bakacağım şimdi. Kosinüs pi artı j sinüs pi gösteriyor. Tamam. Düzeltiyorum. Kafam buraya takıldı çünkü. Düzeltiyorum burayı. Ters yazmış. Kim bulduysa ona teşekkür edeceğim. Arada bakarım diyordum, unuttum sonra. Bakayım kim bulmuş. Erdem, sağ ol. Kosinüs pi. Aa, şimdi bir dakika bunları yalnız ben şuraya bir kosinüs şeyi çizeyim ya. Sinüs sıfır sıfırdır. Sinüs pi sıfırdır. Nasıl oluyor? Burada bir yanlışlık var ya çocuklar. Bunu siliyorum. Bunu siliyorum. Burada bir yanlışlık var. Yanlışlığı da bulduğum gibi hafızaya güvenmeyeceksin. Bunu siliyorum. İnsanın hafızası yanıltıyor. Çizdim. Kırmızı. Aha. Hatayı bulan var mı çocuklar? Ben şimdi düzelteceğim. Şimdi oldu mu? Erdem ne diyorsun? Kosinüs pi bölü 2 sıfırdan geçer. Sinüs pi bölü 2 birdir. Dolayısıyla bu şimdi oldu. Peki. Seyit, e, it's all yours. Çocuklar, my dear students, you think that you are going to take the examination, but that examination is mine. Siz girmiyorsunuz sınava. Benim adıma giriyorsunuz. Yapacağınız her doğru çözüm, bulacağınız her doğru çözüm metodu benim size bunu doğru öğrettiğimi gösterir. Eğer yapamazsanız benim size öğretemediğimi gösterir. Beni temsil edeceksiniz imtihanda. Don't forget that you are going to represent myself. So you have to be successful. Tamam mı? Work hard, think the topics, don't memorize, but try to understand it and become successful. I trust you. Okay, good luck. And I hope it's going to be a good new year for us. All the best. Bye bye. Haydi bakalım. Sen çocuklar çok da yorgun sayılmazlar herhalde Seyit. Sen top sende. Bence.
Yapalım hocam ara vermeden olur.
Başla canım.
Tamam hocam. Hello everybody. Okay, let's start our last lab.
Hocam, there's gonna be a lab or just a quiz?
What?
There's gonna be a lab or it's just a quiz?
We're gonna have lab lost. Let's show it, and we can ask some question to you.
Because I have an makeup exam after.
Which lecture?
I have an exam after like 2 hours.
Okay, no, it will be a short lab.
So
Okay, let's see what you remember, guys. Okay, who can show me? Let's see. I define a nominator. All right. And our denominator. Who can find the transfer function of this? Anyone? Should I choose who? I don't know.
I can.
Hamza, okay. Okay, Hamza. Cool.
I will have to just write the code.
Yeah, you can write it in chat.
So
it's very simple. It's just transfer function.
Just df denominator over denominator.
Come on, don't Google it. That's the right answer.
Just write it.
Okay, let's try it. If then. All right. Nice. Hamza is plus. Okay. Let's say we have a transfer function now. No problem. You're welcome. Okay, now let's say we have a transfer function and we wanted to find the steady state of a transfer function. How are we going to find the steady state? Anyone remember how to find a from transfer function to steady state? Yeah, so that's it. I'm gonna write this. Okay, Hamza, you wait. I just didn't. Guys, anyone else? Omar.
I'm just to give a hint.
Yeah, okay. It's great. Omar, are you here? Omar. Yes, we am. Okay, can you help us? How are we gonna transfer function to steady state? Yeah, Omar, you can send the code district. You can try. You're not sure, just try. How will it be? Okay, let's ask Ali. Ali, are you here, Ali? Ali is AFK. Okay. Erdem? Erdem also not here. Oh. TF2SS. Okay, let's try Erdem. TF2SS. Nothing happened. Tamam yazdık. Sonra başka bir şey olmadı. It didn't work. TF2SS. So you may missing something. See something here like this. Okay. Let's try. TF2 steady state. Mean numerator and denominator, not AB. Ah, okay. Yeah, this is your steady state. Yeah. Like you define your numerator and denominator. You don't need to write the your vector again. You can just write numerator and denominator. Okay, let's go to, yeah, nice. Let's go to our bot diagram. All right. What is bot diagram? It consists two graphs. One is the plot the magnitude of the sinusoidal transfer function, and the other is plotting the phase angle. All right, both are plotted against the frequency on the logarithmic scale. Okay, let's first you're going to define our numerator and denominator, of course. All right. Our denominator, let's say 425. Okay. After you define, for plotting the both diagram, you just write both. In the parentheses, you define your numerator and denominator. This is so easy. Easy comments. When you hit it, it will give you your both diagram. And wait a while. Okay. Okay, the first one is your magnitude. The second one is your phase angle. All right, this is your both diagram. See, very easy. Just define your numerator, denominator, your both. In the parentheses, you define your numerator and denominator again. Okay, let's find another one. Okay, now we can add the title to the graph. Okay, let's define our numerator. All right. 1, 3. Denominator. Okay. Both numerator, denominator. All right, but how can we add title to this? How can add title somewhere here, both diagram? We want to say, okay, this is both diagram of this transfer function. Anyone remember how we add title on a graph? Anyone? Efe? Hamza, wait, you get plus. Yeah, Efe not here. Okay. Amen. Amen. Always, you here? Okay, Erdem, Hamza, Hussein. Oh, everyone leave. Okay, Hussein not here. Muhammad Ramadan. Yes, Hussein here. Okay. Erdem, no, not you. The other one. Okay, can you help us how do we add a title to a graph? So we want to add title here. How we add it in a comment line? Do you remember? Do you remember, Hussein? Okay. God bless you. Okay. Who? Omar. Okay. Raid. Right, Hussein. Right, not here. Yunus Emre. Yunus, sen bize çizebilir misin? Right, you're here. Okay. Can you add a title to our graph here? Yeah. Can you add title to graph? Here we plot the both diagram of our system and we want to add title on top of the graph. It's very simple. Title, let's see. In this. Okay. Nothing happened. Okay, let's open this. First, clear this. Okay, let's define our numerator and denominator here. Right. Denominator. You plot your both diagram. Then, all right. Get title. Okay, that's fine. Yeah, it's empty. Why? Where is right, left? Okay. Yusuf, Selim, Yunus Emre burada mısınız? Yunus sen bize şey yapabilir misin? Şimdi bu grafiğe nasıl ekleriz süre yazı? Bot diyagramını çizdik. Şuraya bir şey ekleyeceğiz. Çok basit. Hatırlıyor musun? Just write in the parentheses. Şu parantez içine yazıyoruz. Çok basit. Bu diagram of system. That's it. Just write title inside parentheses. You define the name of your diagram. Okay, let's go to the Simlink. Now, who Erdem get plus, Hamza get plus, Omar get half plus. Okay, now let's go to Simlink, all right? Let's see what you remember from Simulink. I'm a little bit sick, sorry guys. I guess some of you are AFK. Erdem here, Hamza here, Yunus here, Omar here. Okay. Take a while for Simulink to open. Okay. Now, in the Simulink, we can do the same things with the blocks, right? We have a library here. In library, you have all of kind of the block parameters here. You can find it, for example, here. Continuous, you have derivative, steady state, integrated limiter, all kind of things. You have a simscape for the electrical functions, you see, electrical for the control, you have BLDC control, generator for measurements. You have all kinds of generator circuits, integrated circuits, sensors, sources, power sources. You can just find it all in library. Or you can just double click on the empty space. Then you can write, let's say, for transfer function. Yeah. This diagram will take the transfer function of your input. How we'll do it, when you double click it, you can define your numerator and denominator here. Yeah, let's make it 165. When you hit apply and OK, it will change it. So, can you show me the response of a step a function input? I just want you to add a step function input and show me the output signal of the system. Yeah, do you remember it? Yeah. You can use your mic. You can tell me how to do it.
Thank you, John. I think we first have to add a step block.
Step. Let's see. Okay.
And connect
where?
it to the transfer function.
Okay.
And to see the result, we have to put a scoop block. Scoop.
Yeah. Where? Here.
That's for basic. If you want to make feedback, we have to add the summation and get feedback from the
Add
result.
sum.
Yeah.
Okay. Add sum. Is it feedback positive or negative?
It's positive from step and negative from the feedback. So it will be reversed.
Yeah. So the feedback is always minus, right?
Yeah.
Negative.
And there is a gain
Okay.
or not.
There is a gain if we need it. In where? Where will be the gain?
On the lower side. But it will be reversed,
Yeah.
flipped horizontally.
Yeah, when you click on the parameter with the control R, you just
For
flip it.
control R, yeah.
Yeah, control R, you can flip it. So this is just gain, you can change your gain. Let's make it 5.
And run. We could change the time to 100 or 5 as you need.
Yeah, let's see. Yeah, this is your response of system. You can just do it like this. This is your system response, all right? You
Yeah.
can just double click the scope from here with the settings. Okay, wait. Number of the inputs. We get 2 inputs, all right? And the
Nice.
other one you get from the input, right? You can now run it and compare both input signal and output signal. The one we just get it from input, the other one is the output. Now we can see the changes, all right? This is your input step. Input is the signal where is 1 at 1 and the 0 in
Nice.
other location, right?
It's
So this is
kindly
your
equal
input.
max, right?
Yeah. So this is your input, and this is how your system respond to its input system. Okay, so how about ramp?
Me?
How about ramp input?
We gonna put impulse.
I will just add ramp. The difference is the ramp is the input which increasingly, right? Just increasing by the time. So let's say you delete this, you add this. When you run it, this is your ramp input. It's just increasing, right? This is how your system responded.
Nice.
Yeah. So that was it today. Hamza, you're the only one here. I guess Hamza here. Hamza was here, Erdem was here, Omar was here, Yunus was here. Okay, let me take a note. They didn't get minus, but you guys get plus. All right.
Thank you. So there will be يعني written exam at final or something like that for MATLAB.
Yeah, right. You are here too. Okay. I don't know. In the exam, Nejat Hoca can ask about MATLAB code. It's possible. But I don't know who will he ask or not.
تمام, no problem. Thank you.
Welcome.
Have a nice day.
Hamza was here, Erdem was here, Omar was here. Raid was here. Yunus Emre was here. Anyone? Okay, anyone else? Khalil, you are here too. Okay. Nice. Okay, today Erdem and Hamza get pluses. Amen also here, all right. Okay, today's winner, Hamza and Erdem. All right. That was it today, guys. Let me take a attendance list too. All right. Okay, now take a look at the previous labs too. All right, don't forget it. How do you take transfer functions, steady state, how to plot the step response, ramp response. Yeah, Omar, you can use your mic. No, I have. You have makeup exam for control? No, I don't remember it. I give him Nejat Hoca, but I don't know. Did he consider? Yeah, I remember. I don't know. Did Nejat Hoca give the grades or not yet? You're welcome. Okay, that was it for today, guys. Have a nice day and good luck with your final exam. And today was the last lecture of our semester. See you next semester. Hope so. In another lecture. Thank you, guys. Have a nice day. Happy New Year, guys.